It's easy to forget this now, but around 1900, atoms were not settled science. Chemistry worked beautifully as if matter came in discrete little particles, yet some of the era's most respected scientists insisted atoms were never actually seen, and maybe weren't real at all. The most influential skeptic was Ernst Mach, the Austrian physicist-philosopher who insisted science should only trust what the senses could directly verify. Since nobody had ever seen an atom, Mach argued, treating it as literally real was getting ahead of the evidence. German chemist Wilhelm Ostwald, already a towering figure in physical chemistry, went further still. He championed energetics, the idea that energy, not matter, was the truly fundamental thing, and dismissed atoms as a convenient bookkeeping trick, useful for calculation, not to be mistaken for reality. It's a strange position to hold, given how well atoms seem to work. Fixed ratios and chemical reactions, the entire periodic table, the way gases behave under pressure, all of it fell into place beautifully if you assumed matter came in countable, discrete units. But it works as a calculation, and it's literally true, are different claims, and in 1900 nobody could bridge that gap. No microscope came close to resolving a single atom. The atomic hypothesis remained, technically, unproven, a very useful story nobody could confirm. The mystery that would eventually crack this whole debate wide open was, at that point, already 80 years old. And it had nothing to do with chemistry at all. It began with a Scottish botanist, a glass of water, and a pinch of pollen. In June 1827, Robert Brown, one of Britain's most respected botanists, was studying grains from the flower Clarkia pulchella under his microscope. Investigating plant fertilization, nothing more exotic than that. Suspended in water, the pollen released tiny oblong granules, and those granules would not sit still. They jittered, darted, and zigzagged ceaselessly, with no current in the water, no draft in the room, and no obvious force pushing them at all. Brown's first hypothesis was the obvious one. Maybe these were some kind of tiny living organisms, or the plant's own reproductive vital force made visible. Motion is a sign of life, moving because it was, in some sense, alive. Then Brown tested dead, long-dried pollen from herbarium specimens decades old. It jittered exactly the same. He tried powdered glass, ground-up rock, soot, even fragments of ordinary window dust. Every one of them showed the identical, restless, purposeless motion. Whatever this motion was, it clearly had nothing to do with biology. Brown published his findings in 1828, carefully, honestly, and admitted he had absolutely no explanation for what was actually causing it. The phenomenon needed a name before it needed an answer. What we now call Brownian motion sat, for decades afterward, as a genuine scientific curiosity, mentioned occasionally, tested against a few obvious explanations like evaporation or stray electric charge, and ruled out each time without anyone offering a real theory of the cause. Meanwhile, physicists like James Clerk Maxwell and Ludwig Boltzmann had been building an entire mathematical theory, the kinetic theory of gases, on the assumption that gases really were countless invisible molecules in constant chaotic motion colliding billions of times a second. Boltzmann, in particular, fought bitterly for decades to have kinetic theory taken seriously, against fierce and very public resistance from exactly the energetics camp led by Ostwald. It was, by most accounts, an exhausting, demoralizing fight for a theory Boltzmann was certain had to be right. In September 1906, Boltzmann died by his own hand while on holiday near Trieste. Historians are careful not to reduce a complicated life to one cause. Depression and failing health clearly played a real part. But he died not knowing his life's central idea was, at that very moment, about to be proven right. What the whole debate genuinely lacked was a single, specific, testable prediction, some exact number that only made sense if atoms were real, and that any skeptic could go check for themselves with an actual instrument in an actual laboratory. That prediction arrived from the least likely source imaginable, not a chemist, not a specialist in molecular theory, but a 26-year-old patent clerk in Bern, Switzerland, working through physics problems in whatever spare hours a full-time government job allowed him. His name, of course, was Albert Einstein, and 1905 would become his miracle year, the 12 months in which he published multiple papers that would each, individually, reshape physics. Most famously, special relativity and the photoelectric effect. But a third paper from that same extraordinary year addressed something different, whether the actual, physical existence of molecules could be proven, and, almost as an afterthought, whether that proof might explain a certain restless jittering that botanists had been puzzling over for decades. Remarkably, Einstein himself wasn't fully sure the two were the same thing. In his own paper, he admitted the available data on Brownian molecular motion was too imprecise for him to say. For certain, his theoretical particles matched Brown's real ones, a rare, honest hedge about to be resolved. Here's the heart of Einstein's idea. In plain terms, if water is genuinely made of countless invisible molecules in constant, random thermal motion, they should be relentlessly bombarding any larger particle suspended in that water from every direction, every instant, all the time. Most of those countless collisions cancel out, hitting the particle evenly from all sides. But by pure chance, in any given instant, slightly more molecules strike from one side than the other, nudging the particle very slightly, then nudging it again in a new random direction, endlessly. Individually, each nudge is far too small to see. But accumulated over thousands of collisions per second, Einstein calculated those random nudges should add up into exactly the kind of visible, ceaseless, directionless jitter Robert Brown had described 78 years earlier. Crucially, Einstein didn't stop at molecules cause the jitter. He derived an exact statistical law: the average of the squared distance a particle wanders should grow directly in proportion to elapsed time. Not the distance itself, but that distance squared. Here's that relationship as a real, computed figure, mean squared displacement plotted against elapsed time. Einstein's prediction is a straight line through the origin, not curving, not leveling off, just climbing steadily, exactly in proportion to time itself. Better still, the slope of that line wasn't just some arbitrary number. Einstein showed it depended on the water's temperature and viscosity, the particle's own size, and, folded directly into the formula, on Avogadro's number itself, the count of molecules and a fixed amount of substance. In other words, Einstein had converted an ancient philosophical argument about invisible atoms into something you could in principle measure with a stopwatch, a ruler, and an ordinary laboratory microscope, provided somebody was patient and precise enough to actually try it. That somebody turned out to be a French physicist already deeply invested in exactly this question: Jean Perrin, born September 30th, 1870, in Lille, France, a scientist with a long-standing personal stake in proving atoms were more than a convenient fiction. Perrin wasn't new to this fight. Back in 1895, as a young researcher, he'd shown experimentally that cathode rays were streams of negatively charged particles. Early, direct evidence for the reality of subatomic matter, years before the electron was properly understood. In 1901, Perrin had even proposed, ahead of most of his contemporaries, that atoms might contain a tiny, dense, positively charged core surrounded by orbiting electrons, a nucleus and electron picture that anticipated Ernst Rutherford's later, more famous model by almost a decade. So when Einstein's 1905 papers reached Paris, Perrin recognized immediately what almost nobody else quite grasped. Yet, here, finally, was a specific, falsifiable, numerical claim about the reality of atoms. Not philosophy anymore, but an actual experiment waiting to be run. Starting around 1908, Perrin committed himself almost entirely to this one problem, testing Einstein's formula directly, with real particles, real measurements, and the sheer stubborn patience the task was clearly going to demand. The first challenge was almost embarrassingly basic. Einstein's formula required particles of one single, precisely known size. Ordinary suspensions, dust, soot, ground minerals, came in a hopeless jumble of different sizes, utterly useless for precision measurement. Perrin's solution, gamboge, a yellow resin harvested from trees in Southeast Asia, long used as a pigment in watercolor paint. Suspended in water, gamboge naturally forms small, nearly spherical grains, exactly the geometric simplicity the mathematics required. Even gamboge grains varied in size naturally, so Perrin devised a painstaking sorting method, repeated fractional centrifuging, spinning suspensions over and over to separate grains by exactly how fast they settled, patiently isolating batches of nearly identical, measurable radius. Months of this sorting work produced, at last, batches of gamboge grains of a single, precisely known radius, along with a second material, mastic resin, used to independently cross-check every result against a completely different substance. Perrin's first real test wasn't even the jittery motion itself. It was something quieter, sedimentation equilibrium, the question of exactly how these visible grains settle, or fail to settle, under their own weight inside a thin column of liquid. The logic borrowed directly from an idea everyone already accepted about the atmosphere itself: air is thickest at sea level and thins out steadily with altitude, an exponential balance between gravity pulling molecules down and heat energy pushing them back up. Perrin's reasoning: if gamboge grains were truly being jostled by real individual water molecules the same way gas molecules jostle each other, then the grains themselves should settle into that exact same kind of exponential distribution, a miniature atmosphere made of particles you could actually see. Testing that idea meant hours at the eyepiece, counting grains layer by layer at carefully measured heights within the column. Tedious, exacting work, with no shortcut available except doing it again and again and again. The results came back remarkably clean. Grain concentration fell off with height in almost exactly the exponential pattern the barometric formula predicted. The same law, governing an entire planet's atmosphere, now confirmed on a column of liquid you could hold in one hand. From that precise fall-off, Perrin could work Einstein's mathematics backward and extract his very first independent value for Avogadro's number, the count of molecules in a fixed amount of any substance. It landed remarkably close to the value accepted today. Encouraged, but far from finished, Perrin turned to the harder, more direct test. Not just where grains settle at equilibrium, but exactly how far and how fast an individual grain wanders when nobody is holding it still at all. Working with his collaborator, Mathilde Schadesig, Perrin rigged a camera lucida, a simple optical device that projects a microscope's image directly onto a sheet of paper, and began tracking one single grain's exact position, marking a fresh dot every 30 seconds. Hour after hour, dot after dot, mark the position, wait 30 seconds by the clock, mark the next position, and repeat. Cramped posture, tired eyes, no shortcuts, for as long as it took to build a trajectory worth analyzing. Then Perrin connected the dots with straight lines. The resulting shape was nothing like a smooth, gentle drift. It was a jagged, chaotic zigzag, a random walk path with no discernible direction, doubling back on itself again and again. And here was the genuinely strange part. Zooming in on any short segment of that jagged path revealed the exact same jaggedness all over again, at a finer scale, a shape that never smoothed out, no matter how closely you examined it. Perrin and Schadesig measured the actual distance between dots, squared each measurement, and averaged the results across many grains and many trials, then plotted those averages against the fixed 30-second time intervals between them. Here's Einstein's straight-line prediction again, this time with Perrin's actual measured points plotted directly on top of it. The real data scatters as any real measurement does, but it clusters tightly around the exact line Einstein had calculated 4 years earlier from theory alone. From the measured slope of that line, Perrin computed a second fully independent value for Avogadro's number, this time from actual moving trajectories, not settling grains. It came out remarkably close to his first number, from an entirely different measurement. Two completely different physical phenomena. How far grains sink under gravity, and how far they randomly wander sideways from countless invisible impacts. We're pointing, independently, at the very same hidden number. That kind of agreement doesn't happen by accident. Perrin, meticulous close to the point of obsession, refused to stop there. He reran the experiments with different grain sizes, different materials, different liquids, different temperatures, testing the result from every angle he could think to attack it. Every single variant returned nearly the same value for Avogadro's number. This wasn't a fluke of one lucky setup, it was beginning to look like a genuine fixed constant of nature, hiding in plain sight inside perfectly ordinary laboratory glassware. Word of Perrin's results began spreading quickly through French and international physics circles. Someone had, in effect, found a way to make molecules visible, not through any microscope powerful enough to see one directly, but through careful, repeatable statistics. Across the border in Leipzig, Wilhelm Ostwald, the very chemist who had spent years dismissing atoms as a convenient fiction, sat down with Perrin's numbers and did something rare for a scientist. This entrenched, he changed his mind in print. In a 1909 revision of his own chemistry textbook, Ostwald wrote that he was now convinced science had finally obtained genuine experimental proof of the discrete or grain nature of matter, proof the atomic hypothesis had sought in vain for 100, even 1,000 years. It was a stunning reversal. The scientist who had led the intellectual charge against atomic reality for over a decade was now telling his own students in his own revised textbook that the debate was, for all practical purposes, over. Ernst Mach proved far harder to move. Even confronted with Perrin's numbers, Mach maintained his deeper philosophical caution about trusting entities. No instrument could directly perceive, a principled holdout, increasingly isolated from where the rest of the field was heading. But by this point, Mach's position was a holdout, not the mainstream. Working physicists and chemists across Europe increasingly treated the reality of atoms and molecules as functionally settled, a matter of measured fact, not open philosophical debate. Perrin himself, though, wasn't satisfied with two agreeing numbers. If atoms were truly real, he reasoned, then every other corner of physics that happened to depend on Avogadro's number in its own separate equations ought to point toward that same value too. Radioactivity offered one such road. Radium emits alpha particles one at a time, each producing a tiny flash of light when it strikes a detector screen. Count those flashes precisely enough, alongside the total electric charge released, and Avogadro's number falls straight out of the arithmetic. Blackbody radiation offered a second, completely unrelated road. Max Planck's celebrated 1900 formula for the glow given off by any hot object contained, buried deep in its own fundamental constants, an entirely independent way to calculate the very same number. The viscosity of gases supplied yet a third road, an equation from the kinetic theory of gases, tested in a completely different apparatus, measuring nothing about grains, light, or radioactivity at all, and still arriving in the same neighborhood. Here's why that mattered so much. Any single clever experiment could, in principle, hide a subtle flaw or an unlucky coincidence. But a dozen completely unrelated methods, built from entirely different corners of physics, cannot all just accidentally agree with each other. Here's that convergence as a real computed figure, Perrin's independent determinations of Avogadro's number, plotted method by method. Brownian motion, sedimentation equilibrium, radioactivity, blackbody radiation, viscosity, each with its own margin of error, all clustering tightly in the same place. Every single method, despite measuring wildly different physical phenomena in wildly different apparatus by wildly different researchers, landed close to the same figure, somewhere in the neighborhood of 6 times 10 to the 23rd. To grasp the sheer size of that number, it's roughly how many molecules sit inside a small, single breath of air. Vastly more than every grain of sand on every beach on Earth, multiplied many times over, all packed into something you could hold in cupped hands. Back at his desk in Paris, Perrin gathered years of sedimentation counts, thousands of track dots, and half a dozen independent Avogadro determinations into one single sweeping written argument. The case for atomic reality, made once and for all, in full. In 1913, Perrin published the results as a book, Les Atomes, You. Unlike so much of the technical literature it drew from, it was written plainly and clearly, aimed not just at specialists, but at any scientifically curious general reader willing to follow the argument. The book became a genuine bestseller by the standards of serious science publishing, translated into English as simply Atoms, and quickly became the book physicists and chemists handed to any remaining skeptic who still needed convincing. The book's core argument boiled down: if a dozen totally unrelated experimental paths all lead independently to the exact same hidden number, the convenient fiction defense simply collapses. A fiction wouldn't leave matching fingerprints in a dozen separate rooms. By the mid-1910s, the philosophical claim that atoms were merely a useful bookkeeping trick had, in practice, lost. Physicists and chemists increasingly spoke of atoms and molecules as literal physical objects, with sizes and weights you could state to a precise decimal. The aftershocks reached well beyond physics. Chemistry and biology proceeded with genuine new confidence, teaching atoms and molecules as demonstrated fact rather than convenient shorthand, a small shift in wording that reflected an enormous shift in certainty. Perrin's own career kept expanding well beyond this one triumph. After later helping found the Palais de la Découverte, a science museum in Paris, in 1937, he was instrumental in creating France's National Center for Scientific Research, the CNRS, in 1939. In 1926, the Nobel Committee formally recognized what Perrin's decade of patient measurement had accomplished, the Nobel Prize in Physics, awarded for his work on the discontinuous structure of matter, and especially for his discovery of the equilibrium of sedimentation. In his Nobel lecture, Perrin looked back across the whole 2-decade campaign, patient counting, careful centrifuging, thousands of hand-marked dots that had turned an ancient philosophical dispute into a question of decimal points and honest error bars. Einstein himself, whose 1905 paper had quietly started this entire chain of proof, had by then moved on to general relativity and reshaped physics again. His own Brownian motion paper often overshadowed by his far more famous work, though no less foundational. What's genuinely remarkable, in hindsight, is what this proof didn't require. No particle accelerator, no giant telescope, no exotic machinery of any kind. A good microscope, a steady hand, patient arithmetic, and years of unglamorous repetition were, in the end, entirely sufficient. Revisit the two proofs side by side. Einstein's straight-line prediction for how far a grain should wander, and Perrin's own jagged, hand-traced, random walk path of an actual grain doing exactly that. Theory and experiment, meeting in the same figure. With atoms now established as physically, provably real, the next generation of physics could finally stop asking whether they existed at all and start asking the far stranger question of what, exactly, was happening deep inside them. Today, Avogadro's number is no longer something anyone needs to measure at all. Since a 2019 update to the International System of Units, it's simply defined as an exact figure, 6,2214076 times 10 to the 23rd, the very definition of what a mole of substance means. Here's that same convergence figure once more, with today's exact defined value overlaid, and Perrin's hand-counted, hand-timed, decade-long laboratory campaign, using nothing but a microscope and raw patience, already landed remarkably close to it. Brownian motions underlying mathematics, random walks, diffusion, statistical spread over time, turned out to reach far beyond physics entirely, modeling stock price fluctuations, tracking proteins jostling inside living cells, even shaping modern search and optimization algorithms. Robert Brown himself died in 1858, decades before anyone explained the restless jitter he'd stumbled on almost by accident, a career botanist, remembered forever for a mystery he noticed but never got to solve. And Einstein, in his own 1905 paper, hadn't even been fully confident his theoretical particles were the same phenomenon Brown had observed 78 years before, a rare admission of uncertainty from a mind not often remembered for hedging. It took Jean Perrin's stubborn, unglamorous years at the eyepiece, thousands of counted grains, thousands of hand-marked dots, to finally connect the two, proving a botanist's curiosity and a patent clerk's equation described the exact same real physical phenomenon. Perrin himself was characteristically blunt about what all this had actually cost. Years of eye strain, endless centrifuging of barely visible particles, and thousands of hours spent simply counting and marking, all for a handful of decimal places nobody could argue with. In Les Atomes, Perrin summed up exactly what all these independent, mutually reinforcing measurements meant. The atomic hypothesis had, in his own words, ceased to be a hypothesis at all and become an established, experimentally demonstrated fact of physical science. The broader lesson here reaches well past atoms themselves. Sometimes the biggest scientific questions aren't settled by one single dramatic experiment, but by patiently checking whether many completely independent answers, from many different directions, actually agree. That exact same logic still gets used today whenever scientists need to trust some hard-to-see result directly, look for independent convergence from unrelated methods, not just one clever isolated trick that nobody else can cross-check. It's worth pausing here on just how strange this all sounds from today's vantage point. What elementary schoolers now learn as an obvious, uncontroversial fact was, in 1900, a genuinely open, hard-fought scientific war between some of the era's most respected minds. Imagine Mach and Ostwald's world for a moment. An entire working chemistry that never once required believing atoms were literally, physically, real objects. And yet, somehow, every equation, every measured ratio still came out exactly right, regardless. The deeper lesson, a theory can function beautifully as a calculating tool for 100 years and still leave the deepest question: is this actually, literally true? Genuinely open? Until somebody finally finds a rigorous, independent way to check. Jean Perrin died on April 17, 1942 in New York City, having fled occupied France during the Second World War. By then, his numbers, his book, and his decade of patient dots had already settled, permanently, the very debate he'd spent his career fighting. The next time you see mole in a chemistry classroom, or 6022 times 10 to the 23rd printed on a periodic table poster, remember, it isn't just a number to memorize, it's the residue of one man's decade spent literally connecting the dots. And remember Robert Brown's forgotten 1827 pollen grains too, still jittering today in exactly the same restless way in any ordinary drop of water placed under any ordinary modern microscope, doing precisely what Einstein's mathematics said they should. Perrin's dozen independent determinations of Avogadro's number remain, even more than a century later, one of the cleanest examples in the entire history of science of many completely unrelated roads converging on one single, undeniable truth. Modern chemistry, biology, and materials science all quietly rest today on the certainty Perrin's patient measurements delivered. Atoms as real, as countable, as physically undeniable as the microscope he used, or the paper his dots were drawn on. Thanks for being awake and curious with me today. Share this with someone who's ever been told, with total confidence, that something they couldn't personally see simply couldn't be real. Until next time, keep looking closely at the ordinary things right in front of you, because sometimes the deepest, most contested question in the history of science is quietly settled inside a single drop of water. Stay curious. If this story stuck with you, do two quick things. Hit subscribe. Neat Science brings another forgotten story back to life, and there's a whole playlist of them waiting for you right now. And tell me in the comments which part of this surprised you the most. I read every single one. Your next story is just one click away. I'll see you there.